It's great to be here. In fact, it's indeed an honor and a pleasure. The community around the world that really thinks sincerely and deeply about education at the university, and particularly engineering education, is not that big. I think we talk to each other frequently, and we're always doing this, sort of looking around to see who's got a good idea we can steal. So it's in that spirit that all of this is available for stealing, because most of it I've stolen from Olin. We'll start today. So we're talking about NEET. I've learned long ago that the acronym is important. The students really like to work on a NEET program. The faculty involved are making a NEET future. And it's run by Pekko Asoy, who is my co-chair, now the Associate Dean of Engineering, and Bobby Mitra, who by coincidence we hired more or less off the street in response to an ad, who had just finished in a university in India. So between Bobby and I, we had founded 2 universities or 2 schools of engineering in the last handful of years. So there are academic entrepreneurs. So where do we start? Well, one useful place to start is at the grand challenges, and you can pick your favorite list of them, but this is one, things like sustainability and health and joy of living and energy and so forth. The question I want to raise is, what will our graduates, what will our students do to help address these grand challenges, whatever the specific list is? And I would argue that policymakers will make policy, scientists will discover things about the natural world and unravel mysteries, and engineers will build what I'm calling the new machines and systems. So we have to put ourselves in the framework of the careers of our graduates, which will start in, say, about 2020, and will run through to 2060, 2070. So what are the new machines of this century coming up? Well, by using this phrase, the new machines, it would of course evoke the question, what are the old machines? So since I'm an aerospace guy, I can take pot shots at my own program in my own department, and here it is. On the left, you'll see an old machine. This is a 1950s prototype Boeing 707, was made out of aluminum, was flown by a pilot, his hands on the controls, because of the 1950s that certainly would have been the case. And it was powered by a fairly rudimentary gas turbine engine. Now on the right-hand side is an autonomous drone, which is made of composites and is electric. So now you say to yourself, look at the average undergraduate aerospace curriculum in the United States, or the world for that matter. I can certainly point at mine at MIT in the department that I led for a number of years. Which one of these machines are we preparing our students to build? The left, right? This is the curriculum. Aluminum transonic airplanes with gas turbine engines flown by pilots. And this is what they'll build, or more representative of what they'll build in their careers. So why are we doing this? Well, there are at least 4 factors that contribute to this, let's be generous and say, stability, right? One is the conservatism of the faculty. Trinity College, Cambridge, they say, a little change is good and no change is better. Right? And faculty tend to be sort of in a partnership where the easiest thing to do is more or less to do what we did last year. But the faculty is not the only one contributing to this stability. ABET is certainly near the top of the list, right? Because if you look at the aerospace degree requirements to get ABET certification, you find the picture on the left. And that's what an ABET accredited aerospace engineering program is. And then behind ABET, you find the professional societies, the American Institute of Aeronautics and Astronautics, in my case, which has vested interest in having tags like mechanical engineers, electrical engineers, so that people know what society to join, right? So there are many factors that tend to retard or to stabilize the influence. Now there's another way to think about it, is that just about this time, a bunch of people around the world invented the idea of engineering science. That before 1950, engineering education was largely predicated on a career, an education in practice, centered on design. And after the transformation of the engineering science revolution, engineering education became centered on science, engineering science, where design sort of floated up towards the senior year if the students ever encountered it. So It's not a coincidence, I think, that this stable view of the old machines from the 50s and 60s just happened to be the machines that were around when this education based on engineering science was codified. And it was so damn successful, sweeping throughout the world within 2 decades, that it sort of stabilized or captured this, this model of the machines that we should teach our students to build. So, you know, one thing you can get all faculty around the world to agree to is we've got to teach our students the fundamentals. Right? Then it's just a disagreement about what fundamentals to teach them. So the groups, the buckets I call them, the baskets of fundamentals that we teach tend to be organized around the old machines, which is not necessarily the buckets, the organization of the buckets. Even if we agree the disciplines are stable, it isn't necessarily the buckets of the future. So we know what these new machines will be. They'll be integrated. That is to say, there are very few purely mechanical machines left being built. So there's some combination of mechanical and informational and molecular and biological and energetic. They're complex, right? Because we're asking more of our machines. And by the way, I use the word machines to mean all the constructs of engineers. So for this purpose, new organisms are machines and new code is machines. It's just the phrase I'm using to evoke what it is that engineers build. Not only are they complex, but they're also networked, right? They're all talking to one another, for better or worse. There are high levels of autonomy, and we'd like to have them contribute to a sustainable world. The other way to think about it is it's already 2018. You know, we're approaching 20% of the way through the century. That's a little bit scary, right? We can look into our labs at the great research universities of the world and more or less see what's going to happen for the next 10 or 20 years, because this stuff takes that long to be fielded, you know, everything but software, I would say. So we can actually understand, to first approximation, what the new machines will be. So we decided to predicate the rethinking, the reimagining of undergraduate education based on 4 student-centered principles. This is really important because if you listen to a group of faculty members discuss education, the most common word used in the dialogue is faculty. It's true. I've actually done the word count while I was sitting at meetings because I didn't have anything else to do sitting at those meetings. So these are student-centered. So when I say you, I mean I'm addressing this to the students to prepare you to develop the new machines and systems, right? We've already discussed that one. To prepare you to be makers and discoverers. Makers are people who are synthetic. They build things that have never been. Discoverers are people who unravel the mysteries of the universe as we know it, right? Students will do one or the other of these in their career, or maybe a mixture. But what we've ascertained for sure is that at 20 or 21, they don't know which one they'll do. And they certainly don't want us to ask them to declare that not only are they a mechanical engineer, but they're a mechanical engineer scientist or mechanical engineer designer. So we have an obligation to prepare them across this spectrum from makers to discoverers. The third bullet really reflects on the influence of digital learning and indirectly on social media and such things. We have sort of lost track, I think, about how our students are actually learning. The one fact that was undeniable in the hundreds of students we interviewed as part of this process is none of them buy textbooks. Buying a textbook is a thing of the past. So this sort of this stable engine that you build Curricular around, choosing the textbook and using the textbook. I mean, they may find a PDF of the textbook online, but is happy to find a set of notes from the University of Michigan or an online course from Berkeley and a TED Talk or a Khan Academy. They use this incredible variety of digital tools to support their education, into which we have little visibility. So a third point is to try and shape the education around the ways that they are currently best learning. And the last one emerged sort of organically from the discussions of the committee, which was a realization that an admission perhaps rather than a realization, an admission that the half-life of unused knowledge is measured in months, not years. So what are we really doing worrying about whether the students get the Clausius-Clapeyron relationship in their thermodynamics course or not? What we really want them to do is to learn to think about thermodynamics, right? And so we said maybe there's a set of ways of thinking that we want our students to encounter and absorb and develop while they're at undergraduate at a university. And frankly, I thought when this idea first came up, that we'd make a list of like 3. And we ended up with a list of 11 plus 1. And it was quite a revelation, I'll show them to you in a second, that there are actually these different ways, different cognitive patterns, different ways of thought that we want our students to absorb, and we want metacognition. We want them to know that they've absorbed them. I call them the cognitive toolbox, right? Oh, this is a problem that needs creativity. I'll take out my creativity tools. Oh, this problem needs system thinking. I'll take out my system thinking problems. Or, oh, this is a problem that needs both creativity and system thinking, but at least I'm aware of that, so I can bring out all my tools in those areas. So that's what we mean by the NEET ways of thinking. So here they are. Starting at the lower left-hand corner here, this is humanism, right? This is understanding the role of us in our society, our obligations to society, and so forth. Experimental thinking, know how to test hypotheses, formulate them, look at data, such things. Analytical thinking, learning how to divide problems into smaller problems and apply analysis, often mathematical, but not only. And computational thinking, which at least at MIT is emerging as sort of the 4th foundational way of thinking about the world. And this is not just writing code, this is really understanding how machines solve problems. So it just more or less happens that those 4 appear in the core of many engineering programs, not exclusively. Certainly engineering professors teach a lot of analysis. But for example, by the end of the first year at most engineering schools, you would have encountered analytical thinking, computational thinking, humanistic thinking, and experimental thinking. But I bet that there isn't one undergraduate in 20 that could actually identify that they learned those things and be able to describe how they learned to think about it. What they learned was how to finish the problem set. So how do we switch the emphasis from learning how to finish the problem set to learning how to think in certain ways? And how would you measure it? Great question. So then right in the center is critical thinking. You know, this is what almost all universities in America claim is the mainstay of their contribution to undergraduate education. And of course, there are famous studies that show that the change in critical thinking capability of students from the time they enter university to leave, it doesn't change much. So when you find people in the red states who don't agree that universities are very valuable, we have to actually examine our own conscience on this question. If we really think critical thinking is the most important thing, where is it? Who takes responsibility in the curriculum for teaching critical thinking? Then as an engineer, you start to move up this scale towards creative and system thinking, personal and interpersonal things, making and discovering, and probably the most important, it's 11 plus 1. I never thought this list would get anywhere near 12. 11 plus 1 is learning to learn. This is the idea of the exponentiation of knowledge, the idea that what the students learn in university, even if they learn it well, will have changed by 5 or 10 or 20 years from now in most fields. And we have to leave our students with a very well-honed set of skills to teach themselves over the future. So that's what we call the NEET ways of thinking. And now we have the task of identifying where in the curriculum are the students going to encounter these things, and who's going to teach them and take responsibility for learning outcomes in these dimensions. So we did a lot of benchmarking. This is an evidence-based approach. I've learned over the years that when you want to convince faculty of things, it helps to have evidence. It helps to have rationale as well, but it really helps to have evidence. So we did a lot of evidence gathering, and I'm now the 3rd person this afternoon to reference this report we commissioned by Ruth Graham, who's an independent educational benchmarker in the UK, who has actually done work for both your institution and ours independent of this. And we just asked her to go out and find out what the consensus was about where interesting things were going on in the world in engineering education, and she used the social science approach, which she identified initial targets and interviewed them and asked them who they thought were other interesting sources of information, and the study snowballed to about 80, which were geographically distributed just about all around the world. And she asked 2 questions. The first question was, who are the established universities who you think are leaders in the engineering education business? And Olin came out on top, just a little tiny smidgen ahead of MIT. and Stanford and Aalborg and TU Delft, and then it sort of, the Pareto sort of flattened out by the time you got past those 4 or 5. Independently, she asked, who are the emerging leaders in engineering education around the world? So some people answered, everybody was asked both questions, and of course they would give different answers for both questions. But when you ensemble all the data, it turns out that amongst the emerging leaders, the top university in the world is Olin College. So Olin essentially got twice as many votes in this survey as anybody else in the world. So congratulations. You know, there's no limit to the good you can do if you compliment other people enough. So here these were not so obvious. You know, I knew about Olin, I knew about SUTD, which comes out glowingly as well. I didn't know that UCL University College London had just done a major transformation of its undergraduate education, led by its new president, who came into post about 5 or 6 years ago. Typical Catholic University in Santiago, Chile, where both Eric and I have been on a handful of occasions, right? Really emerges as an interesting case where the government of Chile has invested very heavily in economic development and reformed its university system, and it's sort of the leader within Chile of this university system. It's an interesting exercise, by the way. I'm writing a book on universities, and I asked the question, what's the leading English-speaking university in the world? And you know, you can find it pretty easily. I won't name any names, but it might be places like Harvard. What's the leading Chinese-speaking university in the world? Well, Beida, Tsinghua, and they're sort of in numbers 15 or 20 in the world university rankings in that zone. Those rankings that none of us like, but we quote. What's the leading Spanish-speaking university in the world? And you have to look a long way down the list. So, and what you would find by consensus is actually the Pontifical University in Santiago now. And Charles Sturt, anyone ever heard of it? 1 out of 100. Congratulations, man. Did you read our report?
No. My nephew-in-law is in their informatics group.
Really?
Examining dropout rates and things like
So
that.
Charles Sturt is a university in the outback of Australia, which has gone sort of hard over in the direction of education is going to be online and by internships. So there's essentially no campus and no sort of traditional university structure at all. Boy, were the guys at Charles Sturt happy when they came in the top 10 universities in the world. Headline of the Sydney Daily Mail or whatever it is, MIT finds Charles Sturt best university in the world or something. Now, you know, you'll notice that the first word in that was MIT. So it wasn't bad for us either. I think that this is this performance of Olin in this process was really remarkable. I mean, there's clearly magic going on here to be reflected in this so strongly in this poll. So, so what this did is it gave us a group of universities to go and study in some depth and benchmark deeply, which we did to inform our project. Other observations, shift in center of gravity south into Asia. You know, if you said, what are the great universities in the world now? And if you did the first term Taylor series expansion and said, where would they be 30 or 40 years from now? They'd be moving, that would be the direction things would move, south into Asia. Shift is socially relevant and outwardly facing curriculum. I think that Olin would say that you do that in spades. And emergence of leaders at scale and in long online education, which is to say that the criticism of Olin in the world is, yeah, you can do this for 85 a year, but I've got 3,000. Or if you're at Monterey, you can do this for 85 a year, and I've got 30,000, right? So I think that's our challenge. You know, can we take the quality of education that you have developed and scale it, or create a model which will allow other people to scale it? Or is it in fact something you can do in a boutique with 2 cadres of 40 students each, 2 cohorts of 40 students each every year? I'll leave that for you to reflect on. And then, of course, the other part of it is the online education scaling. So this was the process. Now I've talked about the principles, the new machines, the makers and discoverers, the pedagogy, the ways of thinking, and let's do something worth doing. On the other side was the evidence. So it started out with thought leaders. It used to be hard to get the views of thought leaders. Now you just watch their TED Talks. And I noticed that 2 or 3 times already this afternoon you referred to somebody or another giving. So one rainy Sunday about a year ago, I sat and watched hours of TED Talks on the topic of education. And I'll tell you the 2 messages that really came through from the TED Talks. The less important one, I would say, very important, but it's just number 2 on my list, was the exponential growth of knowledge. That, you know, we've sort of left a linear world where more or less things, if you learned something 20 years ago, it was still valid and valuable. And we've entered an exponential world where the rate of knowledge accumulation is just going faster than any of us can absorb. And how do you readjust an education for that world? Very not an ABET view of the world, by the way. I don't mean to be a critic of ABET, I'm just an observer of ABET. But our actual strategy is we're going to do what's right for the kids, and we'll deal with ABET later. Are you ABET accredited? You are. God bless you. So we did the benchmarking, which I mentioned, largely through Ruth Graham's study, and we did the normal exercises of listening to industry, listening to alumni, a lot of input for students, ate a lot of pizza and gave out a lot of t-shirts to get the students to come. And of course we have to listen deeply to our faculty colleagues. And then the invention occurred, which we call this NEET project-centric model and NEET process. So there are really about 3 ideas here, three constructs, I would say. The first one had already happened by the time we were starting NEET about 1.5 years ago. And it was the development at MIT of what we call flexible degrees. So I'll use a mechanical engineering example because it's easy to relate. The mechanical engineering curriculum used to be essentially dictated. There were only a few courses that students had any choice in, and they had choice from a short list. And you more or less have to do that to get ABET accredited as a mechanical engineering program. So Pekko Hasoi and colleagues at the time working 4 or 5 years ago when I was away in Moscow created these flexible degrees. So a flexible degree has about half of the ABET content of mechanical engineering, and the rest of the content has to be engineering, but it doesn't have to be mechanical engineering. And the degree is accredited in engineering as recommended by the Department of Mechanical Engineering. So it's a very subtle difference. Instead of having a degree in mechanical engineering, you have a degree in engineering as recommended by the Department of Mechanical Engineering. So basically, nobody in the world is going to notice this distinction. Right? I mean, a student's going to go into a job interview, and whichever one of them they have, they're going to say they're a mechanical engineer. But the flexible degree gives them about 40% of the curriculum content to explore and try different things that are not the traditional mechanical engineering content. So now most of the engineering departments at MIT have such a degree program, which we collectively call flexible degrees. So once you have a flexible degree structure, then that opens up the playing field for innovation, because now you can play with this 40% and do interesting things that are new. So that was, I would say, the 0th innovation, in the sense that by the time we started NEET, it had already happened. So the first innovation, or innovation number 1, is having to do with structure of curriculum. So this is what we have traditionally seen. You know, you looked in a catalog and it said, you've got to take Thermo 1 and then Thermo 2, and Thermo 3, and so forth. So that's what this represents, that subject 1 leads to subject 2, leads to subject 3. And potentially a capstone project in the senior year. Most universities have that, and ABET requires it, but it's possible to get out of it and not have a project in the senior year. So this is the NEET scheme, which we call the project-centric curricular construct. So first let me begin by saying that at MIT we don't have control of the freshman year. The schools don't. The freshman year is sort of run by the collective, and all the students more or less take the same thing. So we take as the input students leaving the first year and enter the second. And in the second year, they would have a project. In the third year, they would have a project. In the fourth year, they would have a project, at least one a year. And that these projects would then become the armature of organization of the education, not the courses. And the role of the courses is to teach the things to the students that they need for the projects. So this is somewhat of classic project-based learning, but the projects are designed in such a way that they encourage self-study. So there's a progression of self-study that the students have to develop. There's a progression of digital learning skills that the students have to develop. There's a progression of personal and interpersonal goals and empathy and intelligence quotient, emotive quotient and so forth the students have to develop. And the subject of the string of projects is the new machine. So the way the new machine enters is that it's the organizing focus of the projects. Right? So we started a program on the new machine of autonomous machines. So there's an autonomous machine project in the sophomore year, an autonomous machine project in the junior year, which is the scale of a normal capstone. And then there's an autonomous machine project in the senior year, which we call a super capstone because it's more in depth and broader and deeper than a normal capstone. And then project one motivates project two and so on. So that's the idea of the project-centered curricular structure. Now, I should at this point say something like, thank you very much for having explained all this to us. But instead I'll give you my favorite quote from Carl Sagan, which is that in order to build an apple pie from scratch, you first have to invent the universe. Right? So obviously in the field of education, in particular engineering education, all of us do the same thing, which is we go around and steal the best ideas from our peers, and we put in little tweaks and improvements and hope they work. Right? So I don't want to give you the impression that we invented this for the first time in this project, but the variant of it we invented, which is organized around the new machines, I think is relatively unique. If you went to Aalborg, for example, in Denmark, a great problem-based learning education, you'd find that every semester the project or the problem changes. So one semester they're building a dam, and the next a self-driving car, and the next grid, and so forth. So the distinction here is they always are coming back to the same intellectual topic. The other construct we made is the thread. So universities traditionally have majors, some universities have some minors. We've constructed a third construct called threads. And threads are sort of a pathway from the information technology use of the word thread, as in multi-threaded systems. So the thread is the pathway that you take through the curriculum, and this emphasizes the fact that there are at least 3 projects, and that the students will take some subjects from Department X and some subjects from Department Y. So they're allowed to have interdepartmental programs of their own choosing, or largely of their own design. And the thing that stabilizes these threads are the fact that the threads all go through the projects. So the projects is where all the NEET students come together and work together. So in the old days, a student gets a degree in a major, that's what it says up there. And now a student would still get a degree in a major. Because of the flexible degrees, you can satisfy the degree requirements of these flexible degrees. But in addition, they get a certificate from the dean that says they've completed the thread in autonomous machines or living machines. And this generation of students likes credentials, right? So the idea that they get a second credential for no more work and no more time and no more tuition is a winner for them. It's just a little carrot that's along the way. So this is the concept of threads. And now if you go to the tool, for example, that MIT students use to plan their academic programs so they make sure their courses don't conflict and they've satisfied the right prerequisites, that's all on a database. So there's a pull-down menu that says pick your major, and a pull-down menu that says pick your minor, and a pull-down menu that says pick your thread. Right? So the students are now seeing this in the same structure as majors and minors. So one of the interesting design jobs that you have to do now is you have to say, now we know there'll be at least 3 projects. How do we plan progressions of these skill learning and knowledge learning in these projects, well, obviously they're going to learn about simple autonomy, medium scale autonomy, and complex autonomy. But what else? So how would you use a progression of 3 of them to teach making? Well, maybe they make a simple system without worrying too much about formal design. Maybe they design and build and test a system. Maybe they conceive, implying they engage with stakeholders to derive requirements, build and operate the system. Maybe the way to teach them about interpersonal skills is to have them first work by themselves and then work in small groups and then work in large groups. That's what mechanical engineering does at MIT, right, Woody? Through that progression. But the students actually have pushed back on us on this. They say, you know, we've been working in groups and building projects since we were in 8th grade. And we know how to do that. So why are you going to now force us as sophomores to work by ourselves on a project and not be able to work with others and rely on others? So there's an interesting tension in that bit of design. And then, you know, some things are easy to lay out, like in A you teach the first law and B you teach the second law of thermodynamics. And some things are not obvious, like I put it up here deliberately to be provocative. Personal skills and attitudes. You know, maybe you teach ethics and integrity as the foundational skill and then move on to things like responsibility and flexibility, but this is much less obvious. I would say there's much more open room for design. So what we're doing is we're going through the process of assigning to projects A, B, and C a progression in all of the 12 ways of thinking, the 11 ways of thinking plus teaching by yourself, so that the student will, regardless of which thread they're in, encounter this, more or less the same experiences that help them develop these ways of thinking. So what's the implementation? Well, we started on this in September of 16, thinking that we would do nothing until September of 18 except plan. 2 years of faculty committee deliberations. Second prize, 3 years of faculty deliberations. And we felt such enthusiasm and we developed such momentum that we threw out that plan and decided to pilot something less than a year after we had even started meeting as a faculty committee. And we just sort of asked for forgiveness and said it's all a big experiment and we'll just keep you posted. We didn't go through any of the committees of the faculty. We very carefully crafted this so we circumnavigated all of the structural barriers. We also navigated around most of the rice bowls. Rice bowl management, it turns out to be very important at working at a university. So we launched in September of 2017 these 2 threads. We had a little internal competition, who wants to propose. We got proposals and we evaluated them and worked with the faculty. One in autonomous machines, which now has 31 students in autonomy and robotics, which, I'm sorry for the code here, I just realized this, which is a combination of aeronautics and astronautics, electrical engineering and computer science, and mechanical engineering, 16, 6, and 2. So autonomous machines, self-driving cars, self-flying airplanes, roughly, right? That sort of autonomous system. Living machines is a little less obvious. It's gut on a chip, organs and human cells on chips, which is an alternative pathway to drug discovery and therapeutics to using animal models. Right? There's lots of things that work on the rats and don't work on the humans, so an alternative pathway is to use human systems that are on a chip. So this is the beginning of true living machines in the sense that there is actually living matter that's in a machine that we're using to discover drugs. So we had 12 students in that one, diagnostics and therapeutics, which came from biological engineering, mechanical engineering, and chemical engineering. So rarely does a student at MIT have the opportunity to mix such combinations of courses together. And this is 43 engineering sophomores, or about half the size of Olin. And we turned on the advertising for this 4 or 5 days before registration day in September, and by 2 weeks later we had 43 students who wanted to enter the program, who knew almost nothing about what the program was, except what they read on the website and the student buzz. So what this represents is an enormous potential audience. It's indicative of a strong interest by the students in this sort of thing. Now, let me tell you another way to think about it. You know, at MIT we play sophomore roulette. Do you play sophomore roulette? Sophomore roulette is where you you allow the students to enter as freshmen without designating a major. You do that? And then they choose which major they want to go to. So this is like spinning the roulette wheel, right? You'll let 1,100 students in, and then you spin the roulette wheel and you see where they come out. So if you took the undergraduate programs in the School of Engineering from the bottom in terms of students per year, which is like 6, right? There's 1,100 students. So one of those majors out there has 6, and one of them has 8, one of them has 9, one of them has 15. 43 students is actually more than the 3 or 4 smallest departments combined. So this playing sophomore, and they're all in computer science, right? 450 students out of the 1,100 are in computer science. So there are a lot of department heads and undergraduate committees that saw this number and gasped audibly. We have at MIT arguably one of the finest departments of architecture in the nation. It has 4 undergraduates. 4. You know how many electrical engineers there are this year? Or have just designated as electrical engineers? Not computer scientists, not electrical engineers and computer scientists, straight electrical engineers. 9. So you can imagine an electrical engineering program with 9 sophomores in it. I mean, we have to do something to sort of reallocate the resources and rejigger the system. And I'm not sure the students aren't making the right decision. You know, this year in the machine learning course, out of 1,100 students a year, we had 750 students in the machine learning course. Because of course they all know that this year if they graduate having taken a machine learning course, they'll get a job. I mean, this is not irrational thinking, right? They're actually pretty well plugged in. So the programs that we'll launch in September are materials machines. This is the intersection of inventing new materials and inventing new manufacturing systems to quickly deploy them. So it's between material science and mechanical engineering, and low carbon energy systems, or generating power without producing much CO2. So this is a combination of renewables plus nuclear, right? Which are the non-carbon producing options. So far as of a week or so ago, we had 60 rising sophomores registered, and we're still 3 or 4 weeks from the deadline, the registration deadline. So we could have 100 students in the program this year. So just a few more words about the options. The autonomous machines, which John Howe, a colleague in Aero and Astro runs, has, you can see where the students come from. Only 3 from aeronautics, 17 from mechanical, and 11 from electrical. And here's some experimentation we did. We started out with nothing like a seminar, and within a week we decided to do a seminar on autonomous machines that introduced the technology, research opportunities, and some of the ways of thinking. And then we went over and made a variant of the course that Woody used to teach, 2007, which is more oriented towards autonomy. And we gave the students a supervised module on statics and mechanics and on sensors and robotics, and we provided some interdepartmental space. So the Christmas card you see is an electrical engineer, a mechanical engineer, an aerospace engineer working on a mechanical engineering course in an aerospace engineering lab. Right? And you show that to the dean, and the dean smiles, because such things don't often happen at big universities. So the other way to think about it is, can we structure the sophomore year? Remember that students normally at MIT declare their majors here. Can we structure the sophomore year so that you could take a common sophomore year within the bucket of autonomy and still decide to declare yourself as an aerospace engineer, or electrical engineer, or a mechanical engineer at the end of your sophomore year? So this is intended to answer the concern of the students. How do I rationally pick a major if I haven't taken any courses in it yet? Which is the situation that they find themselves in. So we're trying to delay effectively this decision. So this is what the program looks like. In the sophomore year, there's differential equations, coding, mechanics, signals and systems, programming, and probability, which is not a bad sort of common sophomore year for somebody who's going to go off and build some sort of electromechanical informational system. And they also take the robotics project in the NEET seminar, and then they can choose if they want to be an Aero, an EE, or a Mech-E. And then they'd go on to take some other higher level subjects and an autonomy capstone, that is to say the junior year, and a super capstone in the senior year. So Linda Griffith and Eric Alm proposed the idea of a program in living machines, which has got a much broader intake. Because to build a living machine, you need almost all the skills represented in a school of engineering. I mean, you certainly need biologists, biological engineers and mechanical engineers and chemical engineers, but having some computer scientists around and some civil engineers doesn't hurt either. So we had a smaller turnout, about a dozen students here, but a little less visibility going into it. So they created a seminar on learning machines, and then they used a combination of Europe undergraduate research opportunities and a projects class to keep the students together. So as I mentioned, we're using these existing flexible degrees, the sort of zeroth innovation during the pilots, and we're really about every 3 or 4 weeks checking in on how the pilots are doing and remaking decisions. So instead of having 2 years of faculty committee meetings to decide what we should do for our students, we had a year of faculty committee meetings and a year of just experiments and prototypes. And we're learning much more quickly by doing it that way. So when we asked the students what they liked about NEET, the thing at the top of the list surprised us enormously, and it was community. Also reflecting what Rick said about the needs of our students and the social stability of our students. That, at a big school, there aren't that many opportunities to sit down and talk with the professor and meet with your colleagues, students as colleagues, and work on a project together. And the idea that we had created this learning community was really resonant with the students. Projects early and often, day after registration day in the fall, let's start working on a project. And of course, they like the idea that it leads to good jobs. Another completely unanticipated outcome is the idea that we were drawing in other schools at MIT. So we're now starting to get there's actually, in the low carbon machines, there's actually a variant that goes through physics, through the flexible physics degree. So that crosses the boundary between engineering and science. There's a proposal for small satellites for space observation, which would go between aero and Earth, atmospheric, and planetary science. There's a high probability event of having a sort of smart cities thread, which would go between urban planning and engineering. So this has drawn the other schools, the deans of the other schools, into the NEET program and into deciding on its evolution. And we are deliberately delaying the answer to the question that everyone really wants to know is, what are you actually going to do for a few years? What we're going to do is we're going to run it as a set of pilots until it runs successfully, and then we'll decide, is it an ABET accredited degree? Is it a non-ABET accredited degree? Is it not a new degree and we just continue to use the flexible degrees programs? So we have a lot of options, but we're basically kicking that can down the street, or as I learned at Cambridge, batting into the tall grass. It's one of my favorites. So we've had a tremendous intensification. Don't get me going on vortex stretching here, but we've had a tremendous intensification of the momentum that's been going on around this project. And it's just sort of drawing people in. The Vice Chancellor, who is responsible for all of education, there's a big makerspace movement to provide makerspace and education in makerspaces to all students. And the thing that really baffled me, or not baffled me, but surprised me, is one day the 2 senior people from the MIT library system showed up and said, the libraries want to help. I mean, I haven't talked to anyone at a library for about 40 years. And I don't think I ever talked to a librarian. And she showed up in my office and wanted to help. I said, we must have hit some nerve here. And the school Office of Digital Learning is ODL, the online community, the schools and the departments are all sort of getting sucked in here. Well, I'll finish today with the T in NEET. The T in NEET stands for transformation. So if we're successful in NEET, we will have created some new curricular constructs, some new degree programs, this idea of threads, but that's really not the deepest objective. The deepest objective is to create a structure of a university that will evolve naturally over time and not to create a new one that will stick around for 60 years. Right? And this goes back to the exponential growth of knowledge. So here's sort of the notion of the system that causes the education to keep refreshing itself. which is that it starts with research, and the research and the evolving industrial practice influence the design of the projects. So, you know, this year and next year, the autonomous machines projects is to drive a little car, then drive a big car, and then have a swarm of cars. But who knows, in 20 years or 10 years, it might be, the project might be autonomous operating room robots. I mean, the frontier of knowledge in robotics and autonomy will continue, and the projects will march along with it as being motivated by the research patterns and the industrial practice. So the projects then drive the subjects, because the faculty will observe that lots of students working on the project show up for this subject, and almost no students working on the project show up for this subject. They'll get the message that there's a relevance issue and a timeliness issue, a contemporary nature of the problems. So the projects drive the subjects, which of course support the projects, and the projects prepare the graduates who become young leaders who go into industrial practice, and a few of them trickle back to be researchers at MIT. But we have this sort of closed loop system that is driven by the evolution of the industrial practice and the research frontiers, so that the projects lead and the subjects and evolve on a more quick, shorter time scale, and the subjects, which are more the fundamentals, evolve but on a slower time scale. But the net result is a continuing evolution of the education rather than the situation we find ourselves in for the last 50 or 60 years, which is a fairly static view of the world. Well, that's what I had to say today. I hope some of that made sense.
Terrific. Thanks, Ed. This is really a beautiful architecture for an evolving educational system at scale, which I think is great for all of us to see here at Olin. So thank you for coming and sharing it with us. And then we may have some questions from the audience if you're willing to answer them.
I said enough outrageous things. I hope somebody objects.
Hi. So I wonder if you could talk about maybe the least defined thing, which is the personal part of this thing, and in particular experiential knowledge that students gain by going through really difficult times with a project, whether it's perseverance or when it's actually better to give up. I know last year, maybe the year before, we had a session on grit, if I recall. But you know, it requires a lot of mentoring and a lot of sort of one-on-one understanding. Part of your program that really tries to hit that head on.
It's at a layer below what I spoke about today. But you're absolutely right. I think actually one of the big controversies or the open questions in project-based learning is, do you try to lead the students to be successful, or do you try to lead them to the real answer, which is sometimes you succeed and sometimes you don't? And both sides of that argument, I think, have valid rationale. And you know, it's something that reasonable people can disagree about. You know, the rationale on one side is, you know, they're fragile, they're young, you don't want them taking things on and failing and becoming less confident in their own abilities, less self-efficacy. On the other hand, you don't want to give them the impression that life is full of successes, right? And it reflects itself in the grading argument, right? Should you grade based on procedure, or should you grade on the results of the system they build? So a layer below this, what we've done is it partially addresses your question. We've created a project handbook. And the way we did that is we got together all of the people at MIT who teach the junior and senior projects, and we basically said, what do you do that works? So we sort of gathered in one room, actually in one room over several meetings, the community of people who grapple with these issues on a practical matter from day to day. In that documentation that emerged from that project handbook process, we have some guidance as to what to do. But it's guidance. I don't think there's a crisp answer to that one.
Kitty Didion, I'm curious, with the emphasis on evolving industrial practice and the fact that you now have students being able to go to very different majors and differences like the numbers you said for electrical engineering, what does this do to faculty recruitment and thinking about what happens in terms of how you engage not only the students, but in terms of how you see the whole complex of MIT?
I didn't quite get it.
Well, if you have this emphasis on involving industrial practice and you have students moving more into certain things like machines and other areas, and you have fewer number of students in electrical engineering without the computer science, is there some potential impetus on what future faculty at MIT, what experiences you want, what expectations you have? Because to me, clearly, as a faculty member, I'd be wondering about what is going to be happening to my colleagues and my cohorts in terms of what experiences you want, both in terms of engaging, project-based, but as well as in terms of expertise. And would there be an assumption that they would have had some industrial experience?
Yeah, so let me clarify. The evolving industrial practice influence doesn't necessarily have to come through the faculty, or it doesn't necessarily have to come from the faculty. It has to go through the faculty because they're the ones who make curricular decisions. But the idea here is that there are two sources which are relatively independent of information about what should be in the projects. There's the faculty who look forward through their research and can sort of foresee, or at the frontiers of knowledge, and can sort of foresee the next steps. And then independently, there's the industrial practice, which, you know, advisors from industry would bring to the table. So what we actually have in mind is the idea that there are, let's loosely call them sponsors of these threads, you know, and we're in the advanced stages of negotiation with one great American car company, I won't tell you which one, to sponsor the autonomy thread, or to be one of the sponsors of the autonomy thread, which means, of course, that they get access to the students and they get some influence on the projects. And since the projects have to do with driving with cars, you know, a car company would be a natural. So there is built into the system a mechanism to draw the industry in such a way that they become sort of partners in the projects. Somebody, I can't remember whether it was in your question or your colleague's question, raised the idea of mentoring too, and you also get some value in by drawing in industry by having access to a larger pool of mentors, although alumni work as well. The other question you had embedded in there was, what does this mean about the capabilities of the faculty or how you would recruit the faculty? I have to admit we haven't pondered that very much. I think we're working under the assumption that there's a big faculty at MIT and 10 or 20% of them are sincerely interested in doing things like project-based learning. I mean, at least 10 or 20%. And therefore, there's enough of a pool of people who have or have in the past done project-based learning that they'll be involved. We, in our first year, got 2 proposals from untenured faculty members to lead these threads. And we just sort of quietly pushed those aside because all of us on the committee sort of looked at each other and said, boy, this is really important stuff, but let's let these folks become recognized as successful scholars, and then we'll drag them in a year or 2. So, but it's a good question. I'll have to go back and talk with my colleagues about how the career development fits in. Yes?
You see the entire engineering department moving in this direction, or is it a subset of it? You know,
Well,
what's, you know,
yeah.
what's
So
your view of scale?
I have a model, and the model is that in steady state there are about 7 threads running in the School of Engineering, and they each have a cohort of about 50 in them, because 50 is sort of a nice cohort size, or sort of the largest practical cohort size. So that's 350, 7 times 50. And that would be about half of the undergraduates in engineering in a year. So I don't view this displacing the traditional, you know, degree programs. In fact, it builds on the traditional degree programs, and it requires those departments to still teach courses and to hire faculty and to deliver, to measure quality and such functions. But on the other hand, it puts a significant fraction, 40, 50, maybe even a little more % of the students into the NEET threads. But they would all still appear in the normal roster of students because they're using these flexible degree programs. So, but that's just sort of more of a planning number. So, you know, 350, but it didn't come out of the smoke. It's the product of 2 numbers that are reasonable estimates. One is the largest size for a cohort, 50, and one is, if you sort of look at everything that goes on in engineering, and say, if you did 2 threads, could you cover all of the interest of students in engineering with 2 threads? No. Could you cover all the interests of students in engineering with 4 threads? No. Could you cover all the interests of students in engineering in 6 threads? Now you're starting to get into the realm of the possible. So something in the range of 6, 7, 8 threads, you know, you've created a thread that almost any student in engineering could find one that they were interested in. You know, so 7 times 50 is 350, and that's half the school.
Or should there be a
You're watching the clock.
Yeah.
parallel sort of neat, analogous process or experimentation for people we train to be faculty, who wants to be sort of a teacher or at the university level, and attacking that, forget the word attacking, focusing on that cohort earlier in the process as they want to aspire to develop to be a professor or a faculty, to say, how do we turn those folks?
My answer to this will be radical, which is I don't perceive this as a tension, right? I think that people who are good are usually good at what they do. Right? If they're good teachers, they're good researchers, they're good mentors, they're good committee sitters. I don't find the need to drive a sharp distinction between one type of faculty and another type of faculty. So let me tell you how I implemented this back in the days when I ran something at MIT, like a department, is we would hire assistant professors, and through a hiring process, which is the old one, not the new one. By the way, I stole your admission process for Skull Tech. Did you know that? Yeah, so at Skull Tech we did the Olin admission process. We had students flying in from all over Russia to spend a weekend in Moscow and go through the Olin process, which of course we called the Skull Tech process. But we all steal ideas from each other, right? That's why we're in the business. So I instituted the idea that when faculty members came to speak, they gave 2 talks. One, their research talk, their job talk, and the other is a teaching talk, right? Because I wanted to establish early in the engagement with them that there are at least these 2 responsibilities of faculty, that they should know about research, and they should be able to deliver on research, and they should be able to deliver on teaching. And then if they accepted, I called them up and I said, fine, we'll offer you a position, but I don't want you to come for a year. And I want you to go out and become a real engineer for a year. Take a year's sabbatical from being a scholar and go and work at Boeing. And we did that with all of the young hires over the years, and it continues more or less to this day. And it came back, and almost every one of them said, the year away transformed my view of research. Because I spent a year at Boeing learning what the real problems of airplanes and spacecraft are, rather than the imaginary ones that professors tend to make up. And now I'm going to orient my degree, my research work, towards the real needs of industry and society. So I think that you can shape people, and you can influence their attitudes.
20 to 30% adopted, the rest will sort of come along.
Yeah.
That's how you get it.
So I feel it's a workable problem. I don't feel it's in my top 5 problems to worry about.
Thank you very much. This is quite fascinating. On the ways of thinking aspect, one consequence of knowledge changing so fast implies that the traditional focus on content, meaning methods and tools and so on, is, let's say, short-lived. However, what's enduring typically and less variant, not quite invariant, but less variant, are the concepts. Mm-hmm. So to what extent have you identified the core concepts that need to be learned for life through these various threads? And I'm thinking of concepts like, say, for instance, corner conditions, feed forward versus feedback, a prototype before production, that sort of thing that really sticks with life no matter what changes with the content later on.
Not much. It's a really good point. And it's another one of these things that's sort of a level below or 2 level below the problem I'm working. Because I would think that any group of faculty would be constantly engaged in that intellectual thought process and discussion about identifying the important concepts in their field, and let's make sure that the important concepts are covered. Eric's in the front row, right? So, I have a famous chart that I show. We do peer instruction with the clickers in our sophomore education, and with concept questions that we've made up for aeronautics and astronautics. And there's a classic question where, you say you've got a box, and out of the box there's a thread, and it's attached to a weight, and the weight's going up. What can you say about and it's in a gravity field, what can you say about the energy in the box? And it has to be going down, right? And you ask this concept question, and 10% of the students say, the first law doesn't apply to this situation. I mean, I'm trying to teach thermodynamics, and 10% of the kids in the room think the first law doesn't apply. I mean, these are really deadly conceptual mistakes, right? So we've tried over the years to build an inventory of concepts for the types of engineering that we teach, but it's not stable. I don't know if I ever told you this, but we once had a whole committee that said, let's identify the concepts that we teach in roughly information sciences and autonomy. And they worked on it for a long time, and they sort of came back and said, most of the faculty members have different conceptualizations of the problem. And it's hard to find a common one so that you could explain stability and feedback control systems to all students so that they all got it. One professor has a sort of more mathematical way of thinking about it, one professor has a more mechanical way of thinking about it, one more has a more boxes and arrows system thinking way of thinking about it. So it's a tough question, identifying the underlying concepts.
I realize that, and perhaps it is too granular for this conversation, but in essence, my concern is similar to the gentleman earlier asking about the personal aspects. We all have faculty that loves the content and is very wedded to the content, and unless we identify the concepts and the competencies and make them very visible, they really never get paid attention to eventually.
Well, on that point, I completely agree with you. I mean, I call it the tyranny of content. It's what we spend most of our time arguing about and most of our time teaching, which is probably not as relevant as some other things. Now, what I was worried when you were halfway through your question that you were going to ask me about is how we're going to develop the concepts that underlie the ways of thinking. How do you teach critical thinking, right? And how do you teach creative thinking, and so forth? And that we are working on. So I was prepared for that question.
Happy to volunteer what we have on that topic.
Yeah. Oh, well, let's go in the back. Does someone in the back have a? Yeah. Are you a student?
Excellent. Thank you for the presentation. As a Olin student, there were a lot of things that I recognized and identified with, and I think that's the information stealing in all directions, and that seems to be good. One of the things that I sort of particularly identified with and noticed was this idea of a progression from individual to group projects to large groups, and from sort of canned projects that were the missions given to you to more open-ended and that sort of thing. With sort of a notable different property at Olin that we tend to do that in the first semester rather than over 3 years. And I'm curious, when you're designing a plan like this, what trade-offs you're making about a sort of shorter, more iterative, every class going through that process individually versus doing it as one overarching story, and how you made that trade and how we can be influenced by that.
I have an answer for that question. Thank you for giving me one that I can hit out of the park. There's a difference in what you can do in a small, cohesive faculty and a larger, more distributed faculty in terms of assigning responsibilities for learning outcomes. So I've learned this the hard way. I got a couple of scars here, a couple of scars there, where I've tried to do more or less what I think you just described you do at Olin, which is have, at a more local scale, more of the stuff integrated into subjects. What happens at our university, and I suspect most larger universities, is that works because you get Professor A who wants to do it that way. And Professor A starts teaching, let's say, creativity as part of something. And then a few years later, Professor A rotates out of that class, and Professor B rotates into it. and B is much less interested in that stuff. So it goes away, because there's no curriculum police at a university. There's actually nobody who comes and certifies that, you know, what the syllabus said was being taught in a class is actually being taught in the class, right? So as a completely structural issue, it's actually easier to keep control over it and do a quality process on it if you have more discrete, concentrated nodes where the students encounter that sort of learning than if it's sort of spread out all over, which is not necessarily the optimal solution, but is a solution robust to the real environment, which is the fact that faculty roll over every 3 or 5 years teaching.
I think that makes a lot of sense.
That's not a happy, but it's a satisfactory answer.
Thank you.
Thank you very much, Ed, for a fascinating discussion.